When discussing signal sampling, nothing is more fundamental than the Shannon-Nyquist sampling theorem. If you want perfect reconstruction of your original signal, you need to sample at twice the rate of the highest frequency contained in that signal. Otherwise, you might get undesirable artifacts such as aliasing. To illustrate the importance of this, I've created a very handsome 10 kHz cosine function to sample at, below, and above the Nyquist rate, which I have plotted here. Already, you can probably see what will happen to the undersampled sinusoid. When we use an interpolator, the signal is completely lost when sampled at 10 kHz. It's just a constant magnitude line. When sampling exactly the Nyquist rate, the shape and frequency of the signal are more or less preserved. When sampling at 3 times the Nyquist rate, the reconstructed signal still looks like a sinusoid. And it turns out no matter what method you try to reconstruct, this will always be the case. The zero-order hold reconstruction here has the same benefits and problems we saw in the interpolation case. So, since creating false information as a result of aliasing is always bad, we can only ever obey Nyquist. This must be all we know. Or is it? Through compressive sampling, we can sample below the Nyquist rate. Any signal can be represented as a linear combination of basis functions, such as the discrete cosine transform. In this case, C will be largely zeros or a sparse matrix, somewhat analogous to random sampling. Similarly, the process of sampling is defined by its own separate basis functions. Here, phi defines the subsetting of the original signal f with respect to sampling. So we need to solve this equation, ax plus b, if we want to recover this original signal, as defined by these equations. However, the system is undetermined. Even MATLAB can't decide how to solve ax equals b, even using 2 equivalent ways to solve this equation. The solution, ultimately, is to minimize the L1 norm of the solution with respect to the original signal. Unfortunately, diving deep into the topic of L0, L1, and L2 norms is outside the scope of this video, but the advantage of L1 is that it's linear computable. Let's try with a more complex signal. This is the tone that is played when the A key is pressed on a touch tone telephone in both the time and frequency domains. At its core, it's the sum of 2 sine functions, which you can see the frequencies of clearly on the frequency plot. There are 5,000 total samples, and I have selected 1,250 of them at random. This is well below the Nyquist rate for a signal of this size. When running it through the L1 optimized solution pipeline, I was able to reconstruct the fundamental frequencies, albeit at a slightly reduced magnitude. This can be transformed into a much smaller, albeit somewhat noisier version of the signal. I will now play both, first the original and then the reconstructed signal that has been boosted to have around the same volume as the original. It's noisier, but if you listen carefully, it's the same note.